Hello, and welcome to another episode of Talking with the Experts, the video podcast where we chat with thought leaders about today's growing natural hazard risks, like wildfires, floods, lightning, and yes, severe storms. I'm Mike Nichols, your host and AM's content and social media manager, and today we're looking at cutting-edge science related to the observation and forecasting of hail, which seems rather timely since we're now in peak hail season for the U.S. To help me, I've invited two top-notch researchers onto the program today. First up, I've got Dr. Jacquelyn Ringhausen. She comes to us from AM's research and development team. So, hey, Jackie, thank you for being here. Really do appreciate it.
Yeah, thanks for having me. I'm always up for talking about lightning or weather in general.
Awesome. I think you might get a little chance to talk about all of that. Dr. Ringhausen, she joined AM last year as a postdoctoral lightning researcher. Since receiving her PhD in lightning physics from the University of Alabama in Huntsville back in 2021, she's built quite an impressive resume as a field researcher. She's interned for both the National Weather Service and NASA. She's helped deploy a variety of environmental sensors into the field. She's designed and built lightning sensors, tested their detection efficiency. She's even helped run a field deployment to collect 3D lightning data inside Hurricane Ian. So today, her focus will be on discussing the connections between lightning and hail and how those connections can be leveraged to create early warnings for hailstorm.
And a fun fact, that hurricane deployment, Sean was the other person helping run it, one of the other people.
That is so cool, yeah, which brings us next up. It's Dr. Sean Waugh. Sean, thank you for being here.
Yeah, absolutely. Always happy to chat with you guys.
Not exactly coming to us from that usual office location, are you?
No, we were actually on the road today. Hail is one of those things that never stops. You know, it occurs in a lot of different places and times of the year. So we're actually on the road headed to Northwest Oklahoma, Texas, Oklahoma Panhandle, Southwest Kansas, that kind of region to see if we can find some hail.
Very cool. Very cool. So Dr. Waugh, he's been a research scientist for NOAA's National Severe Storms Lab since 2016. And he's also a real-life storm chaser, as he's doing today. And speaking of storm chasing, here's a fun fact you may not know about Sean. In addition to having done some previous deployments with Jackie, he served as a behind-the-scenes consultant for the movie Twisters. He's developed a pretty slick new tool to capture more accurate hail observations, and he's going to be talking to us about that. So thank you, Sean, Jackie. Really appreciate you both being here. Should make for some fun conversation. Speaking of fun conversation, it's also a little known fact that Dr. Ringhausen, she tends to have some pretty eclectic lightning jokes. And I made her promise that she'd share one of those with us today. So, Becky, what do you got for us?
So I actually decided to go with a hail joke since this is a hail-focused one. Super cheesy. Okay, so the joke is, how are onions and hailstones alike?
Sean, any ideas on your end?
I'm gonna go with the Shrek-based answer and go that they have layers.
Yeah, so that's one part. They both have layers, and they both really stink when they hit your car.
Yes, they do.
Although I guess if you're Sean, he might be wanting that, so.
Right.
Very, very
That's true.
Hilarious.
That's a great way to start us off. With that, we're going to try to transition into the serious part of the conversation. And so, Sean, since you're our outside guest and also you got a lot going on your plate, we're going to go ahead and get started with you right away. So let's start off just having you tell our viewers about this new device.
Yeah, so hail is one of those things that's really interesting from a damage perspective in the U.S. Everybody tends to focus on tornadoes and hurricanes, and I mean, rightly so, those do a lot. But hail actually causes about $15 billion a year in damage, which is a lot. It's a lot more than tornadoes, actually. It's very widespread. You know, you don't have to have 5 or 6 inch diameter hail to cause a lot of destruction and to cause a lot of insured loss and things like that. It's also one of the more difficult things to study. It moves very quickly. It breaks everything that it hits. You know, it's very difficult to observe. So up until very, very recently, all of our observations of hail are post-impact, where we find something on the ground, we sample that afterwards, and you know that's how we make the connection with a lot of what's going on in the real world is to what we find 20 minutes later. But those stones have melted, they've broken, that's not what actually fell. So what I've done is build a system that's capable of observing those stones in complete free fall. And I'm sure we'll get into this, but the rough details, shoots 4K footage at 330 frames a second. We're using high-speed cameras to try to slow-mo that hailstone on its way down, and we can figure out things like size and shape and fall speed in 3 dimensions. And in order to do that, we need a lot of light. So the LED array I have puts out about 30% more light than the sun. So please don't park behind me, don't tailgate me, anything like that. But it is intensely bright. But we can use that system to get a completely new and unique, one-of-a-kind look at hail that's just going to fundamentally change our observations of hail going forward.
Wow, that is so cool. We'll get more into the design, but I'd just love to know what the development process for something like this is like. Is this something that came to you in a moment of just brilliant intuition, or was it just sweat and perseverance, piecing it together bit by bit? And how long was the whole process?
Probably a little bit of column A, a little bit of column B, right? So a couple of my colleagues and I, hail's been one of those things that's fascinated us for years. And for me personally, it's a huge challenge because there didn't exist a system that was capable of doing those observations. And I really thrive on those kinds of challenges. So we got together and we were like, hey, if we're going to tackle this problem, what do we need? Well, we need observations of hail on the way down. Well, how do we do that, right? We build a camera-based system so that we can see what it looks like, just like we were watching it with our own eyes. Okay, well, that sounds easy enough. Then came the hard part, actually putting it together and building it. And honestly, where we are today is the culmination of about 3 years worth of effort, a couple of early prototypes to kind of work out the kinks of the system and build up to the current version of the truck. When I started this truck the way that it is now, it took about probably 6 months to actually build. Most of that is the coding because none of the software to run this existed. I've had to code the entire data collection and the analysis side of that from scratch. So it's not just meteorology, it's engineering, it's wiring, electronics, it's software design, it's the whole thing.
I remember seeing the beginnings of it when I was there, and I'm glad to see it out and actually taking videos, so that's awesome.
Yeah, it's been exciting to see it finally come together and be something that we can take out into the field and see all that effort start to pay off with some of the images that we've already collected.
So let's talk about that. How has it impacted your ability to make those hail observations? What are some of the specific differences you're seeing now?
Yeah. So one of the things that, obviously we're still processing the data, we're still collecting that data, but we've already been able to capture and process images of stones on their way down. I have a GIF that I shared on social media a few weeks back that's an almost 3-inch diameter stone. It's falling at 66 miles an hour. So for the first time, I can actually calculate what the downward velocity of that is. And that's real. That's not a theoretical stone. That's not a wind tunnel test. That's real world, right? I can also tell you that that stone was moving sideways at almost 30 miles an hour because it was getting pushed by the horizontal wind. So now we know deflection. But more importantly, we can watch that stone as it rotates, as it moves through the atmosphere. It's not melting, right? There's no water streaming off of it. So that's really important if we're trying to ascertain what that stone looks like to a radar. So that's really getting back to that core motivation of improving our ability to detect and warn for these types of events. And then the stone just utterly smashes into the bed of the truck and it shatters into 1,000 pieces. And that's really, really critical because if you're only looking at what you find later, you would never know that stone existed. You'd see the dent and then wonder what caused it, right? But we can actually see that stone on the way down and see its shape and how it had a lot of different sections to it, and that's just one stone. I'm only talking about one stone. We run this for a few minutes. Each camera produces over 100,000 images and over 100 gigabytes of data. I mean, we have tons of information. In 4 days, I collected 2 terabytes worth of images.
Oh my gosh.
So we've got a lot to go through still. We're just scratching the surface.
So when you're looking at these, do you find that they always break up? Because I'm thinking about the world's biggest hailstone. So right. Is that just a piece of a hailstone and it was actually way bigger?
Yeah. So you're talking about the Vivian record, which I think was 7 or 8 inches. I mean, at what point does that really matter? It's huge.
Yeah.
It weighed almost 2 pounds. It fell in Vivian, South Dakota in 2010. That's what they found. So I can promise you, looking at that stone and seeing how smooth it is on certain parts, I guarantee you it was bigger. There were parts that either melted or broke off when it landed. So that's what we found. What was it on the way down, right?
Yeah.
Was it 8 inches, 9 inches, how much of that are we missing? How fast was it falling? Was it rotating, right? We
Mhm.
assume that hail kind of orbits in a random fashion so that to a radar it looks like a sphere. I don't actually think that's the case. Some of the stones that we've been seeing have a preferred orientation. So there's ZDR, that differential reflectivity return that we usually look at. That's going to appear differently. It's not always zero ZDR means big hail. That's definitely not true. So there's a lot of fun things that we're going to be able to get out of this.
So you're coming out, parking your truck under this massive hail coming down at, you said 60 miles an hour, right? So, and making this huge dent in the truck, and you're carrying this high speed, expensive camera and massive LED light kit on the back. What are you doing to protect all that?
Yeah, so obviously having a really high-end camera like that, you don't want to get it hit by hail. I don't want the camera to break. They're pretty expensive. So the cameras themselves, along with all of the LEDs and the wiring, that's all in a metal box that's reinforced with steel on the corners. It's got a polycarbonate lens on the front. That's 1/4 inch thick polycarbonate. It is bullet resistant to like 9 millimeters. So hail, we're gonna get dents for sure. But those cameras and all of the system that's basically running that data collection is very well protected, as is the rest of the truck. I mean, we're parking in front of this thing. I don't want my windows getting blown out, right? I need to be able to move. So all of the vehicles that we have a hail cage on top that's made of this wire mesh. It allows us to move around in those environments pretty freely. I've tested that cage up to about 6.5 inch diameter hail, and it bounces off of it like a trampoline. It's actually really funny to watch.
Wow, that's amazing. So, Sean, what's the plan? So you've got this incredible observation mechanism and you're taking some great observations, terabytes of data. What's the plan going forward? Are you looking to deploy more of these in the field? Is this going to be a one-off?
Yeah, great question. So right now, this is the only system like this that exists. Jackie's certainly very familiar with creating unique equipment and observations and things like that. And the idea with this is that you create one, you test that, you make sure that it's defendable, you know that you can trust the data, and then you scale from there. So with this system, obviously, we're getting it out into the field, we're collecting data, and we're going to be able to change the game with hail observations, put that back into warning information, forecasts, all of that. But going forward, we have plans to build more, and not just more exact copies of this one, but I got a few tricks up my sleeve that I haven't shared yet that the next system is going to make this one even better. We're going to do even more with that next system, constantly one-upping it and making sure that we're pushing that observational limit forward. So over the next couple of years, you're going to see a few more of these getting out to the field.
So you're free
I'm
not to
excited.
answer, but I have to ask since you brought it up. Can you tell us any of those next tricks up the sleeve?
So if you've ever watched sports, NFL does it, MLB does it, a lot of those higher end sports do it where they switch from a camera, like straight lens perspective to a 3D reconstructed environment. They're using multiple camera angles at the same time to digitally render that space. I'm going to do that in the back of this truck. So one of the goals that I have is to use multiple cameras to try to capture singular stones on the way down and do a complete 3-dimensional rendering of that stone in total free fall so that we get a complete 3-dimensional view of it. You can calculate, you can make estimates of density. So now you can do mass and all that kind of stuff. That's the next goal, is to try to, get a system that's capable of doing that. And I can tell you, it is not easy. This is a challenge for sure.
Have you thought about doing anything with like the base of it? So what material the hail is hitting and testing, how the hail breakup changes based on the material, or adding in electric field measurements, electric field change, like a plate where you can actually measure the charge of each of these hailstones.
So we are probably going to put some materials in the base of the truck. One of the things that I actually want to do is put like roofing panels in the bed so that we can do the imagery of not only the stone on the way down, but how it's actually causing that damage.
Yeah.
Jackie, I think you mentioned this earlier, with these stones, like we're seeing different size stones or the same size stones in the same environment. And each one that breaks, they break differently.
Mhm.
Some of them don't break, they bounce, that's obviously a density difference or an impact angle difference, but that translates into damage on your roof. So if we can get materials like that in there, where we can actually see how those stones are causing that damage, that just makes our job that much easier and helps the insurance agency and building codes and all that kind of stuff going forward. So we are talking about adding a few things. All of the electric field meters that I know of right now, I do not think would survive the hail that I typically drive into. Most normal people aren't there. I'll put it that way. So if we can get a hardened one, absolutely. Let's put it on the truck.
Makes a lot of sense. Hey, so and you've already touched on this a little bit, but go a little bit further. So what impact do we see these observations having over time? You mentioned the insurance industry. You mentioned building codes. What other impacts do we see these having?
So most people, if you're sitting at home and you got a weather service warning that pops up, it's on your phone, your computer, the news, whatever, you want to know whether your house is about to get hit by quarters or softballs. There's a big difference between those, right? And it can sometimes be very difficult on radar to tell the difference between those. So from a warning standpoint, from the weather service offices that are producing those life-saving warnings, if we can get better at detecting hail, of distinguishing the different types of environments that produce that hail, the different radar signatures for different sizes and velocities and things like that, then what we're doing is we're immediately improving that warning process. We're getting more accurate warnings with better lead times so that we can protect life and property in front of these types of events. Further downstream, if we can get better at understanding how hail works and falls and forms and rotates and all this, we can ingest that into our modeling assumptions so that when we're forecasting these events 2, 3, 4, 5 days out in advance, those models now become more accurate and more meaningful. That way we're getting a better sense of what's about to happen. And that's the idea with all of this data, is to improve that warning process, that forecasting process, so that we can help the public better prepare for these events.
Yeah, thank you, Sean. That makes a whole lot of sense, right? There's a lot we still don't know about hail, and filling in those gaps, ultimately, it's going to make us a lot more resilient against hail. Although I think it is worth emphasizing, as much as we don't know, there is still a fair amount we do know about hail formation. So, Jackie, you know something about that connection between lightning and hail formation, right?
Yeah. If you're thinking about the ingredients that create both lightning and hail, they have a lot of overlap. So one big ingredient is updraft strength. If you want a lot of lightning, you want a strong updraft. If you want large hail, you need a strong updraft. So, if you're thinking about these big chunks of ice floating in the sky, in order to stay up there, you need some sort of strong upward wind keeping them to counteract gravity, pulling them back towards the earth. You also need ice and water, and you need this to be lofted below the freezing level so that your hailstone can collect and freeze and grow. And the stronger your updraft, the more lift it has, so the larger your hailstones the longer they can stay up there and the larger they can get. Now with lightning, a similar thing. So if you have a very strong updraft, you're going to get a lot more collisions between all those ice crystals, your graupel particles, and your hail, and your super cooled liquid water droplets. And when these collide, they exchange charge, and that's how you get charge in your cloud. And typically, gravity is what's separating them out, so your heavier particles will be lower in the cloud and your lighter ones higher up. Another unique thing about updrafts is they're very turbulent, especially on their edges. And this creates these pockets of charge that you'll get. And so you'll have negative and positive right next to each other. And this can lend to having a large increase in your lightning rates. So there'll be very small lightning, but there'll be a lot of it. So you'll usually see a strong increase in lightning when you have a very strong updraft. And again, you have that ice and that graupel and that super cooled water, which all of these ingredients overlap with your hail. They don't cause each other, but they are correlated to each other because they have similar ingredients that they want in order to occur.
So, dumb this down for me. Basically, the correlation is
more collisions when you have an updraft. That's what's happening, and they're exchanging charge. And then for your hail, you need that upward lift. So that's what's keeping it up there.
Right. And so, as I understand it, then, because of that correlation, you can actually use lightning activity as an indicator of storm severity and probability of events like hail. Is that correct?
Yeah, they're definitely correlated, and often there's been lots of studies that have looked at lightning jumps, is what they call them, and you'll see this increase in lightning before you see a severe weather event. And again, that's because a lot of these severe hazards like hail, potentially tornadoes, strong winds, are correlated to having a strong updraft in your storm. The types of storms that have strong updrafts typically produce severe hazards. So that's how you can use it. However, it's not a 1-to-1 ratio. So you're not going to say, oh, I got even more lightning, so there must be even bigger hail. And there's some caveats with how the hail is growing. So if you have wet hail growth versus dry hail growth, if it's wet hail growth, when you have those collisions happening, a lot of times the ice crystals will actually stick to the hail and they won't bounce back off. So you're not getting as much charge buildup, and the lightning's not quite as correlated to those regions. So it's a complicated problem, but they're overall in general related to severe hazards is an increase in lightning.
And that wet and dry growth, just to jump in here and feed off of that, is really important if you're looking at things on the surface, right? I've seen 6-inch diameter hail that's solid ice. It basically looks like it came straight out of your freezer. I've watched those kinds of stones hit the asphalt and bounce without breaking. They're so dense, they just ricochet off the asphalt. And then 2 seconds later, another 6-inch stone hits, same size, but it's on the lower density side, and they just splat on the ground like a snow cone. So depending on which one of those hits your roof, it causes a very different amount of damage.
I can imagine.
For sure. Yeah.
So if you guys could guide me a little bit, though. So that's the relationship between lightning and storm severity, but I understand radar also gives an indicator of storm severity. Give me some comparison and contrasting. You leveraging lightning activity to make some judgments versus radar.
Well, radar, it's been around for a very long time, and we've had a lot of time to study these signatures. So Sean's already mentioned some signatures, like the ZDR values being near zero. So ZDR is called differential reflectivity. It's kind of looking at the shape of your hydrometeor. So if it's longer, like if you have a raindrop, they're usually shaped like a brain or a kidney bean, you're going to get a higher ZDR value. In hail, a lot of times you'll see the tumbling is what he's talking about. And if it's tumbling, it looks like a circle. And so it'll have a 0 ZDR value on a radar. However, that's not always actually the case. And there's a lot of caveats that go into that. If I was looking for hail, I would be looking at reflectivity. So if you have really high reflectivity values, and especially aloft, you want to look above freezing. So if you're seeing these high reflectivity values above freezing, it means you have some pretty large ice happening up above, and that's probably a hail signature. You can also look for something called a hail spike. So it's a 3-body scatter spike. This is with very large hail. And it's kind of like if you see your normal radar signature, it's an echo that extends outward from that strong reflectivity cord, and it looks kind of spiky and straight. It's caused by that radar beam hitting the hail, and then some of it gets reflected into different directions, like the ground. Then it can reflect back, hit the hail, and then come back to the radar, and this causes this false echo, so it's not actually raining there. So that's one, like if you see that, there's a good chance that there's hail. Like that's a dead giveaway if I'm looking at radar.
That's good to know. Thank you, Jackie. That's really helpful.
I will say, even though I tend to focus on what's falling at the ground, lightning can actually be a very good precursor to things that are about to happen. One of the terms that we've kind of been using in the last several years are things like lightning jumps, where you have this big increase in lightning activity, especially CG type lightning activity that we can see a lot of times in storms where we start seeing that lightning activity increasing substantially, where it's a notable change. What that usually means is the storm is kind of taking a big breath, where it's pulling in a lot of air. That air is going into the updraft. That updraft is causing more of those particle collisions that Jackie talked about. And that's causing more electricity to generate and more lightning to form, right? Usually that is a precursor to some sort of severe event that happens. So if we start seeing that lightning increase, that storm's just generally getting a little bit stronger. Maybe it's about to produce a tornado or, another 6-inch hailstone that makes Sean happy when it lands in the back of his truck.
AM, we actually have a product along those lines, right, Jackie?
Yeah, we do. So we have something called dangerous thunderstorm alerts. And again, this is based on what we just talked about. So if there's large increases in lightning associated with these strong updrafts and these severe hazards, you can use them to alert people that, hey, there could be an increase in the severity of this storm coming your way. So basically, these dangerous thunderstorm alerts, they track lightning. They look both forward and backwards in time. And by doing this, they can actually give you the location, the size, the speed, and the direction of each of these cells that it's tracking. And it can also track like the flash rate changes. So is there a big jump happening? Is there a decrease happening? And you can think of it kind of like a warning that severe hazards could be happening in the future. And they're especially useful if you're in a region that doesn't have radar data, for instance. and all you have is lightning, because our lightning data is global, so we can use it in regions that might not have the accessibility of our radar. You can also embed it with other data sets. So we have something called Elements 360. And with this product, it's very customizable. You can add in, your radar, your lightning, your surface obs, and you can customize what data you see based on your needs. So it's really handy. Like, if you want to look at flood warnings, you might not need lightning data, for instance, and you can add in your river levels and your surface ops. It's also been used for wildfire research and also severe storm hazards and monitoring. So it's a pretty cool tool.
And I can see how the lightning data would complement the radar data really nicely, right? So,
Yeah. Usually that's what it's used for. Like in the Weather Service, when they're forecasting, a lot of the lightning data is like almost a secondary confirmation. So they're looking at the radar, like, is this going to become severe? They see some signal, but they're not entirely sure. And then they see this jump in lightning and they're like, okay, I feel a lot more confident in issuing this warning.
makes a lot of sense.
Mhm.
So I know we could go on, but I know, Sean, you are out driving who knows where throughout Oklahoma right now. So you guys have an incredibly busy schedule. So I want to wrap this up. And to do that, let's just let each of you give us your final thoughts on what you see as the current state of hail observation forecasting and where you see it in coming years. And Sean, since you're our guest and also you're the most likely one to break up because of where you're at, let's have you go first.
Okay. It's always helpful when somebody says, you should go first. That way we don't have to figure that out. So I mean, hail observations, it's getting a lot of attention right now, right? Like I said earlier, hail causes a lot of damage. There's an NSF funded research project that's going on right now called Ice Chip that's bringing together a number of people that are actually looking at hail. It's really starting to be a focal point, especially from people that are paying attention to how much damage it causes, that sort of thing. So I think over the next couple of years, especially the next 5, definitely, you're going to see a lot of attention being paid to that. You're starting to see people really shift, but not just so focused on the tornado problem anymore, but on this whole severe storms problem in general. Tornadoes, hail, lightning, wind, flash floods, all of it, right? So I think as technology has improved, we've gotten a better handle on how we can attack these types of problems. Hail camera is a really good example of that. Going forward, we're going to continue to push those observational limits forward. That's what NSSL does at its best, right? Is pushing that capability forward, creating these new tools and equipment that we can then distribute to the rest of the community, and everybody else wants to start using it. If everybody can build another hail camera, then great. The more that we have out there, the more observations we're getting. And we're going to use that information and those observations to get better at that warning process and that forecasting process that I talked about. So I think there's a lot of excitement and attention that's being played to hail, like currently. I think that's going to carry forward for a while to come.
That's so exciting. Hey, Jackie, and that means you get the final word.
Obviously, these innovations like Sean's hail camera and phased array radar are great stepping stones towards getting better at being able to see hail, know what's going on. And when you think about hail observations and reports right now, they're not the best, because people will pick them up, like he said, it might be 20 minutes afterwards, measure it, and they might not remember what time it actually happened. So when you're trying to correlate what's going on to what happened, it's very hard. But I think the big thing we really need is better observations of all the hydrometeors inside of the cloud. So Sean right now is getting the bottom part, which is very useful. And then I think the next step will be actually being able to see what's going on in the cloud. And that's going to be a very hard task, but I think that's going to be in the next 10 years what's going to push forward our understanding of both hail and lightning, because seeing those interactions and what hydrometeors are happening and what concentrations can tell us what kind of lightning is happening, what charge structures are happening. And so I'm excited to see what's going to happen in these next 10 years or so.
Well, that makes so much sense. That is exciting. You guys get me excited talking about it. So, that is it for our time today. I want to be respectful. Jackie, Sean, thank you both for taking time out of your schedules to be here. And thanks to all of you for tuning in. Without you, there is no program. I found today's discussion incredibly entertaining and eye-opening, as always. I hope all of you did too. If you'd like to learn more about dangerous thunderstorm alerts, head over to our website at aem.eco and look under alerting hardware. More on Dr. Sean Waugh's hail camera I can say the Boston Globe just did a really great article back on May 1st. I'd encourage you to check that one out. And until next time, this is Mike Nichols for AM and for Talking with the Experts.